is a subset of GL2R. So what is this? This is basically A in R2 by 2 such that the determinant of A is equal to 1. All right? And so I guess in terms of our current technology, it's not obvious that this is a manifold. All right? I don't think it's obvious. But let me write down a coordinate chart on this one for you. So if we think about A equal to A, B, C, D, right? Those are real numbers. And what do we know? We know that AD minus BC has to be equal to 1. Right? So let's say if A is not equal to 0, then apparently we get AD is equal to 1 plus BC. So D is equal to 1 plus BC over A, right, in that context. Okay? So there's a subset of SL2R, which is subject to this condition that A is, non-zero. And so if we let U equal to A, B, C, D, such that, AD minus BC is equal to 1 and A is not equal to 0, then if I want to define the chart X on A, B, C, D, what should I do? Well, I suggest we do the following. This is going to be kind of boring, but here it is. A, B, C. See, now this is the context where I have to pay the piper and be like, I'm going to take the viewpoint that this is a topological space, and as such, I need to prove that my chart is a homeomorphism. Like, that's a more convenient viewpoint to take for this example. Like, well, can't you make up? It's a theorem that those viewpoints are equivalent, right? So I can be sloppy and go back to the other viewpoint. The question is, why is this invertible? I mean, it's clear, well, I think it's clear, that this is a continuous bijection, right? Why is that? If I put the images of two different matrices which are in U equal, then I get equality of the A, the B, the C of the two matrices, which then forces the D to be given by this equation over here. So the two matrices are equal, it's injective, it's an injective map. All right. Equality of three indices paired with the determinant 1 condition forces equality of two matrices, is all I'm saying. What's the inverse of this map, and why is it smooth, or why is it continuous? So what's the inverse of this map? What's X inverse of ABC equal to? Well, I'll do the easy part. A, B, C. And the more interesting part, of course, is right. And so, anyway, once we get everything set up more concretely here, these calculations, I believe, suffice to prove that. Now, it doesn't prove that SL2 is a manifold, right? But this is an example of a coordinate chart on SL2. Does it cover all of SL2? Well, no. Because SL2, of course, has matrices where A is 0, right? But if you look at, you could of course do a similar thing for the matrices where B is non-zero, right? Or where D is non-zero, or C is non-zero. You can get charts for each one of those different cases. And if you take the union of all of those, you've covered all of SL2R. So you'd have an atlas in this way, something like that.
Is it a maximal atlas?
No. Maximal atlases have infinitely many charts in them. We almost never will furnish an actual maximal atlas. Like this is the sleight of hand that we do. We produce a finite atlas, and then we say, well, that defines a smooth structure because basically those, you adjoin to that all possible compatible charts. But there are places where we want to assume that we're given a maximal atlas for the sake of proving a theorem,
So even though it covers all of the SL2 because it's not contained in the first chart, it's not maximal.
Right, yeah, I mean, because there are additional charts which would be compatible with those and yet aren't those. Like, for example, I can restrict. Like, I could look at matrices such that, like, not just A is not 0, but A has to range between, like, 1 and 2, not inclusive. That would give me some open subset of SL2, which is smaller. That'd be like a restriction of atlas. I can take essentially I can take essentially arbitrary restrictions of that chart and still get a chart. Yeah.
When you were saying as long as we have an atlas, we know there exists a maximal atlas.
Right.
Is that why we can define manifold in terms of atlas instead of maximal atlas?
Yes. Yeah.
So is that atlas, is an atlas that covers the whole space equivalent to the maximal atlas on that space?
Well, I mean, he says that.
If you tried to do stuff with it, I don't think I know how to ask this.
It's okay. It says, like, here's definition 1.27 in Jeffrey Lee's book, right? It says two atlases are said to be equivalent, provided that their union is an atlas. And he says a differentiable structure in M is an equivalence class of CR atlases. All right, so, like, what's the notion of equivalence? The notion of equivalence is compatibility. In particular, when you take the union of the two atlases, they're compatible. So, like, and that's what the maximal atlas is. It's the equivalence class of atlases. So it's a set of atlases, which I think at the level of charts is the same as saying you're taking the union with all possible compatible charts. Like that's.
So it's just a set.
Yeah. So. There are, of course, more examples, obviously. Let me just use words for a second here to talk about the other examples for today. Like other examples include spheres in n dimension, right? You can talk about spheres. You can talk about example 5. So, oopsie. So example 5, you talk about this, the n sphere, which is a subset of Rn plus 1. The n sphere. Example 6, another example of a manifold is so-called real projective space, RPN. And RPN is more complicated. It's defined in terms of equivalence classes of lines. So that is not something I can, but anyway, that is another example of a manifold. And it's in all the books, like it's in both of the Lee books, and these seem to be the standard examples everybody shares in their basic manifold theory book. This thing I did with SL2, that's weird. Nobody does that. So real projective space, it's a manifold. You can also do it with complex projective space. real projective space. And that's an interesting example because it requires you to do things with equivalence classes, which is always good for math majors to get more comfortable with working with equivalence classes. Things are well defined, all that jazz. It would make Dr. Sperano happy to see us working with RPN, right? What else? Well, theorem. If M1, M2, dot, 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 dot. Let's just do M1 and M2. If M1 and M2 are manifolds, I can't spell, manifolds of dimension N1 and N2 respective. Goodness gracious. Then M equal to M1 Cartesian product M2 is called the product manifold. And guess what? It's a manifold, all right? And how do you build its charts? What do you guys think? Like what would be the atlas for M? What do? You just do, what you're gonna do is you do U1, let's say, let me say, I'm gonna put an upper index for a change, U1 alpha cross alpha 1. Fine, I'll do alpha beta. I'll make a choice eventually, guys. U2 beta, comma, X alpha cross, I'll say Y beta for the sake of annoying notation. And I regret the 1 and the 2. I'm going to change to U and a V just to be annoying. All right, such that U alpha, X alpha is an element of the atlas on M1, and U beta, V beta rather, Y beta is an element of the atlas on M2. So basically you just take the product of the charts. And you can prove that in fact this is a brand new manifold. And its dimension is what? This right here, like, so like if we take X alpha cross Y beta and we let that act on the Cartesian product of U alpha with V beta, how's that work? Well, how that works is you have X sub alpha of U alpha, Cartesian product with Y sub beta of V beta, right? And this right here is a subset of R N1. And this right here is a subset of Rn2, and subject to the usual identifications, namely like concatenations and deletions of vectors, which we do all the time, taking for granted, not thinking about. I'll tell you what, you try to computer code it though, you'll notice. This is Rn1 plus N2, okay? It's N1 plus N2 dimensional. So that's pretty, so look, we can take any open subset of a manifold, a new manifold. We can take, if we have two manifolds, we can take their Cartesian product. We make a new manifold, right? It's pretty cool. Easy way to generate new examples. You can do super weird stuff like take the Cartesian product of a sphere in real projective space. That gives you a new manifold, which is both, all right? Another example, 7. You could let your manifold be something like, let me say M. We could do something like 0, 1, Cartesian product with a manifold N. This would be a cylinder. You could say a cylinder over N, right? And the chart on this thing, it's something like we take the real number t and we take the point, let's say P and N, And what do we map that to? We map it simply to t, comma, y of p. We're assuming here that p is an element of V, which is a subset of n, and that, basically V, comma, y is chart for n containing p, right? So if you want to build a new manifold, which is essentially a stack of an existing manifold, you can just take the Cartesian product with an open interval, and that will give you a cylinder of manifolds. So we can easily generate like a one more dimensional manifold, which is just a stack of one we already have, which is kind of neat. Hard to picture if that's like a four-dimensional manifold, but doesn't stop us from doing it, right? Example 8. The one sphere is important. So the one sphere we can just look at as e to the I theta, such that theta is in the reals. That's a subset of C, which we think of as being identified with R2. Usual complex analysis thing, we take the complex plane to be R2. This is the unit circle. This is the standard circle, S1. What's a chart on the circle? If I have x of e to the I theta, how do I define it? I mean, a circle is a one-dimensional manifold, right? What's the chart on the circle?
Part of the edge.
I mean, there's your point. What's the coordinate on that point? There's not one answer. This is an ambiguous question, right? Because there's a 2 pi degeneracy for theta. And of course, we can't let the chart can't cover the totality of the circle because of that we'll have a fall from bijectivity if we do that, because of the 2 pi periodicity of the exponential. So like, we're going to have to do something like it's theta, and we're assuming, like theta is an element, for example, of say 0 to 2 pi. Mm-mm. Then we have discontinuity. You can, for the sake of calculations in complex, sure. Right up until you want it to be holomorphic all the way around, right? Because then you get that, the actual jump, which is the problem. But there you go. I mean, in other words, pick your favorite argument function, throw out the endpoint that we're not going to use. That's a chart on the circle. All right? That's a chart on the, so the circle is a one-dimensional manifold. If you can do that, then you can define this as well. See example 9. T, we can do, say, S1 cross S1. It's one of my favorite manifolds. Right, one of these, oh man, I forgot how to draw my donuts. Oh, rats, I'm just not, oh there, that's not it, there we go. I'm not happy with my donut today. Anyway, so a torus is a 2-dimensional manifold, right? And you can use the angle around the small circle and the angle around the large circle as coordinates. Now here's something. Eventually in this course, I want to get to the point of explaining to you that this torus, depending on your notion of distance, can either be thought of as a flat manifold or a curved manifold. See, there's a non-standard notion of distance that we can define on the torus to make it flat, to make it have essentially the geometry of the plane. On the other hand, if we just give the torus the geometry which is induced from 3 dimensions by restricting the 3-dimensional notion of distance to the torus, it's certainly a curved space, as your intuition would suggest. So there are all kinds of exotic notions of distance that we can induce on curve sets that will sort of defy intuition, all right? That's a comment for much later in this course, but I think it would be a shame for us not to do those things since we're building the machine that makes those things make sense, yeah.
When you say curved, is that related to what we learned in geometry of like obtuse triangles have?
Yes, it would be related to studying triangles on the surface, yeah. But like more generally, the question is, a manifold is curved if it has a curvature tensor, which is non-vanishing. Well, a curvature tensor is something that's rather complicated. It's a type 4-0, or it has 4 indices, let's say, all right? And the curvature tensor vanishes for flat manifolds. Anyway, I'm not sure we'll get to that part of the story in this course, honestly, all right? But especially not if I keep burning class time and not telling you things. Let's see here. Any other examples for today? Of course, you can talk about the n torus. Like you can keep taking more tori. In Cartesian product, you get a higher dimensional torus. All right, you can do that. Yeah.
How do we know that there is that ring shape? If we're, I mean, am I correct in saying that the cross product happens with, or I guess, Cartesian product happens with like one?
Well, this picture is a mnemonic. It's not really honest. I mean, as a point set, T as I've constructed is S1 cross S1, right? What did I just say S1 is literally? It is what? It is a subset of complex. So this is actually a subset of complex 2 space, also identified with 4-dimensional space. So this, to be fussy, the torus that I just built here is in 4 dimensions. So like a physical torus that we might talk about in calculus 3, this is not as a point set the same thing. Although of course you can obviously make a one-to-one bijection between that and this, right? So I guess that's probably a good place for me to like try to like tell you where we're going next class and kind of like try to chop it off here. We got to stop at some point. And I won't be able to go overtime on Thursdays because there's a piano lesson I have to get my son to at like 5:30. So don't worry. I only will blather on Tuesday in class. But so in topology, what you're going to learn is the fundamental question is, given a set and another, given 2 different sets with 2 different topologies, the question is, are those actually the same thing topologically speaking, right? If they're the same thing topologically speaking, we say they're homeomorphic. To say 2 sets are homeomorphic is to say that their topologies are equivalent, that there's a one-to-one bijection between those, and that bijection is both continuous with continuous inverse, all right? So in some sense, the problem of topology is the problem of identifying whether or not 2 sets are homeomorphic. The problem of manifold theory, the problem of differential geometry, is taking 2 sets and deciding whether or not they're diffeomorphic. So what does it mean to say 2 sets are diffeomorphic? Well, diffeomorphism, we haven't really defined yet. Diffeomorphism means that your 2 sets, there's a bijection between the 2 sets, right? And that bijection is smooth with smooth inverse. So to say that 2 sets are diffeomorphic, right, would be to say that they have the same smooth structure, right? And so if you start reading either of the Lees, and I'll send an announcement out to try to clarify what I expect of you guys. But anyway, it's interesting. There is like up to diffeomorphism just one smooth structure on Rn, if I remember right, for n not equal to 4, if I remember right. So you can get, it's slippery. So like somehow the equivalence class idea that we're talking about, it settles. I showed you that the cube map doesn't have a smooth inverse, right? Like that gets addressed in terms of the equivalence. I can't say it today. I read it. I had it straight in my mind and it's gone again. Anyway, so what's interesting though is in 4 dimensions, there are infinitely many different smooth structures on R4. 4 dimensions is weird. And that's why there is tons of active research in there. It's small enough dimensional that interesting things happen, but it's just this confluence of like not being super big, but not being so small that things aren't possible, that it has lots of freedom. It's hard to explain exactly why God has created math in such a way that that happened, but it did. And it's actually very interesting because that has to do with physics, because in physics, if you're talking about physics, you're talking about fields. A field is a function from space and time. Well, space, there's 3 spatial dimensions, there's 1 time dimension. You see, so sections of 4-dimensional manifolds are actually very interesting because they have to do with space-time. So, like the problem of classifying and saying what happens in 4 dimensions is actually very interesting for physics, and it's a deep and open, interesting question. I have a whole book that's about this thick. It's called The Wild World of 4 Manifolds. I haven't read it, but it's sitting somewhere in my dusty shelves waiting for me to find and read. But my student from Alabama has actually gone, he's at Texas Austin now, and he's, at a place where they're actively looking at the topology of low-dimensional manifolds. And he did an REU on like knot theory and things, so that's part of the reason I know about some of these things. But anyway, so next time we need to talk about what is a diffeomorphism, what does it mean to have a smooth mapping from one manifold to another, and so we'll do that. And then of course, past that, we need to talk about like what's the tangent space and so forth. And I think I'm going to try to more or less follow the flow of Jeffrey Lee's book, and I think the homework problems in there you guys are going to enjoy more for the most part, because I think that there's about 60% topology homework, at least in the early chapters of John Lee's book. So that doesn't work since you guys haven't had topology, except for you, Ernesto, of course. But sorry. Anyway, thanks, guys.